Okay, let's get started. What we're going to do today is solve problems based on failure theories, which we've talked about in the past few classes. Here's a typical problem. I would say that last time when I taught this, students had a difficult time understanding the concepts here, but what we are going to do here is important because this is critically what you need in order to solve problems in the exam, also to design machine elements. That is, given a structural element which is loaded in a certain fashion, you want to figure out what the stresses are and what are the critical points. Again, so I'm just going to attempt to explain these to you. Okay, so I'm assuming you've downloaded this question from Blackboard and just get started. Okay, let's read the question. A force F is applied at D as shown. It's right here. Assuming that the material is ductile and the critical point for failure is A. Okay, that's now given to you, but most times you'll have to figure that out. Compute the value of F, assuming maximum shear stress theory and B, distortion energy theory. Assume that the yield strength is 81 kpsi. So we are given SY, it's 81 kpsi. Okay, so what's happening here is this is the usual questions are you are given the force and you are either told to find the factor of safety or design the element. Here it's the reverse. You're given the strength and you want to find how much F this can apply in this particular situation before it fails. And since there's no factor of safety, we just assume that it is 1, which means that the critical stress for failure is SY. So with that, let's try to solve this. So we've told that A is the critical point. So what we need to do here is we need to identify what are the stresses at A. So this is our stress element at A, sigma x. So you can see that this stress element now will be in the x z plane. So sigma x, sigma z, and then there would be shear stresses. That would be, in this case, tau zx. Okay, so once I identify these stresses, so identify sigma x, tau sigma z, tau zx, then I need to compute the maximum shear stress. Tau max and sigma prime, which is the von Mises stress. And then of course, if things are not to fail, then the maximum stress will be sigma max and sigma prime would be sigma max, where sigma max is equal to SY because the factor of safety is 1. Okay, so this is basically the framework. The part which is, I think, the hardest is number 1. This one is the one which people normally struggle with. How do you compute sigma x, sigma z, and tau z? So I'm going to try to make my best to explain to you how do you do that. And then once you do that, the rest of the stuff, 2 and 3, it's pretty much plug and chuck. The formulas are given, you can just apply the formulas. So let's try to compute these stresses. Okay, so just make a copy of this. Quick second. Okay, so again, I'm going to draw the stress element at A. So Cx, and that stress element looks, well, it looks something like this.
Professor, I have a question.
Sure.
So how are you saying like that's tau, like sigma z is just you're taking the z axis on top? We can say like that's y too, right? Like how you're saying this sigma z and sigma x?
Oh, sure. So you can see this axis. The axes are Z and X, and A is on the top. So it's oriented along the X Z axis. And so this is not in XY, but in ZX plane, because the top face of A is in the ZX plane and not in the XY. Or is that what, if I'm understanding your question, why XZ, why not XY?
Yeah, that's the
Yeah, so because of the way this axes are defined, that's all.
got it. Makes sense. Thank you.
Okay, yeah, so now let's do step one, which is compute sigma z, sigma x, and tau cx. Now, we know that if a beam, let's just think of this like a beam, is loaded in this fashion f, then this f will induce a bending moment. So the whole thing will have a moment, and that moment would be the force time. In this case, it's going to be the distance from A all the way to the point of application of F, which is here. So from A all the way to C, and that distance is 12 plus 2 or 14. Okay, so that force essentially causes a bending moment. The other thing which this force causes is that it causes a shear stress. If this force is applied, it's going to, so this moment is in the mz direction. So the way to think about movements is if you curl the fingers of your right hand along this direction, then your thumb gives the direction of the moment. In this case, the moment is clearly it's negative. It's in the negative z-axis. So this is along negative z-axis. Use right hand. Okay, and that is kind of important because unless you have that sense, you are not able to compute sigmas. The next thing which this force does is it torques this machine element about this axis. So there is a torque this way, and that torque is going to be about the x-axis. That torque, we can compute that torque to be F times the distance of B to C, but in the direction of the z-axis. So that will be 15. So that torque, again, take your right hand, curl your fingers along this arrow, and that gives you the direction of the thumb gives you the direction of this torque. So that torque is in the x direction. So we have, to summarize, we have mz equals 14 times f and tx equals 15f. So this is probably the most critical part. You need to do this, and just by using knowledge of statics, right? Force, distance cross force is the moment. And then you can think about it as no more moments which will come because of the way the force is applied. Okay, so now once we have those forces, now we can ask, what does M induce? M typically induces a normal stress. So if this is AB or AC, and then if there's a moment this way, then we know from our theory for moment, bending moment, and normal stress is that this, we just draw this quickly again. That's it. And then this moment is this way, and it's m z. And then let me draw the neutral axis, which for this case is going to be right in the middle, because this is the geometry of that is because it's basically a shaft along that axis. So now we have to compute sigma. In this case, this is going to be sigma. So if you apply mz, then the stress would be in x direction, right? Sigma x. So this is z, that's x. If you can think, you're observing this from this side. You're seeing it from this way, and that's what you see, and that's the picture. X is along this direction, and z is along that, and so sigma x would be mz. Now the distance is going to be along the y-axis, along this axis. So, and that distance is measured from the neutral axis divided by I. The moment is, let's just put I. Okay. So m is known. We need to compute y and I. Y is d divided by 2. The maximum stress occurs at the outer surface. And the inertia, this is a table. It is pi d raised to 4 divided by 64. And then we check that. Okay, 64, yeah.
Professor?
Yeah.
I have a question.
Yeah.
So for the torque part, I'm just a little confused that so the torque is applying on the D cross section, the circular cross section on the D side. That's where the torque is applying, basically. Like I'm just like a little confused how it's pointing towards the x-axis.
Sure. So just put it this way. So if you have a beam and you have a force, that force will cause this thing to turn, right? So this, I'm just looking at the torque now. This distance is L. So this is the force. And so this force will cause about this axis. It will cause this lever arm to twist. And that would be F times L, right? The L is the distance from the axis. So the best way to think of this is you've got to look at it from here. If you see it this way, then you'll see essentially something like this. Force L, and so that will cause torque, which is F times L. And that direction happens to be in the x direction. This is x, this is z. Okay, so this is a 2D figure. This is the top, the bottom one is the perspective, but if you do the side view from the way that you see it from the right side, then this would be, since this is y, this is z, this torque is in this direction, which we are used to. We never really talk about torques in 3D, but really the way this torque is applied is it's about the x-axis. Because the way torques work is you need to curl the fingers of your right hand along this. So when you curl, your thumb would point in the direction of tx, and that's just the interpretation of torque. It should be tx. Is that clear?
Professor, I have a question.
Yeah.
So you're saying if like if this whatever it is, it's rotating like counterclockwise. So we are just like pointing our right hand fingers in that direction, and then our thumb is pointing to the x direction. That's why torque is pointing to the x.
Yes. So that's right. So I mean, the other way to think about it, and now that we are getting back to statics, which is if you have I. This is a unit vector along the x-axis, unit vector along the z-axis, and unit vector along the k-axis. We know that I cross j is k, right? We know this for a fact that if you take the cross product, it is k. What moment is actually r cross f is the, in this case, it's a torque, and we need to put the appropriate values. So if you use this logic here, r is L. Okay, this vector is this way. So that is in the k direction, crossed with the force. The force is acting in the downward direction, so it's acting along negative y. So I would put f j. So it's f L times k cross j, but k cross j is I with a negative sign. And so it's f L cross I. So you see that it is along the x-axis, along x
Makes
direction.
sense.
So now this is, I think this is just a long part. You're taught this thing in I don't know, in 12th grade or whatever you taught this, but this just takes so much work to actually do this. The easier way to do this is to just curl your fingers along this arrow, this direction, and automatically you'll get the direction of Tx. That's just a shortcut. But if you prefer this route, vector mechanics, this is how you do it. That's it. But remember that it's r cross f and it's not f cross r. This is the key formula. Okay, let's get
First,
back.
just a follow up.
Sure,
So how
sure.
did you get for the moment, the mz thing?
Oh, sure. We can do this similarly. It's exactly the same.
Yeah. Oh,
so it's exactly the same. Let's do it. So you have this and this force. And we'll call this L. Let's call this L1. In this case, what we're trying to do is, okay, let me put the axis. So I believe this is X, this is Y, this is Z. So in this case, we are taking moments in a different way. Our R is L1 times, this vector is along the x-axis. So I crossed with F, we already saw that it's along the negative J. And so it'll be F L1, negative sign, I cross J, but I cross J is K. So this is the torque. This thing is R, this thing is F. And so you see that it is, it's along the K, so I can show it here. So since it's along negative K, I need to draw it in this fashion. Because when you curl your fingers from the right hand from here to here, from the left to right, your thumb will point in this direction. That will be M Z. So I believe I wrote similar expression. Let's go back. Yeah, I wrote MZ. Yeah, I wrote MZ, but I did not quite do it this way because it just takes so much time to write this. If you want to be, I mean, this is, some people like to do this with cross product. Some people just like to visualize it. If you want to do it more generic, then what you need to do is this, and this is like the way you would do it with a software package. You don't want to do any visualization, you just want to give formulas. Then you need to write this as R, and that R is L1. So this is getting both these components in one shot. L1 is along I, and then L is along J, and F is negative vector J. And so really what you're doing is, to find the torque, you're doing R cross F, which is L1I plus LJ crossed with a denominator somewhere. This is not J, this is K. The L is along this direction. It should be K crossed with F, J. Okay, so you'll have L1 F I cross J. That's the multiplication, and then plus, minus F times L K cross J, which is negative L1 F I cross J is K, minus FL K cross J is minus I. So this part is, this is the moment about K, it is mz, and this is moment about, well, it's the torque in this case, right? Because it's going to be floating, so it's Tx. And so if you prefer this, that's, you can do this. This is probably more, you don't really need to do any intuition, and you don't have to do any sort of visualization. You can just plug it in that formula, which comes from statics. And use it.
This makes a lot of sense, Professor. Like, so in this case, we will get like the moment and the torque in the directions, like whatever our axis is. Makes sense.
Right.
Okay. Thank you.
Yeah, sure.
Thank you, Professor.
Yeah, no problem. Okay, I never thought that it did that way, but if you like, go for that. Okay, now I've wrote down formula for sigma x, and there is a d in that. Now there are two places I can apply d. There is, since you've been told that a is here, it's not really clear if a is this point or this point, right? We've not been told. It could be, it's the kind of ambiguous here. I did not really put up, I put in myself this square. So we have to make a choice whether we need to use the bigger diameter or the smaller diameter. Now, we've always said that smaller the diameter, higher the stress, because sigma is inversely proportional to d. So if you want to really figure out where the critical, where the stress will be maximum, you want to choose the cross section with a smaller d. And so we will choose d equals, let me see, d is, it's blurred, it's 1 inch diameter and 1 inch. We'll look at the figure again in mind because yeah, it's 1. That's the one we'll use. This is the critical D. Smaller. Okay, now we've also, in this formula, we've made an assumption. We've assumed that there is no stress concentration, but in reality, when you have a stepped shoulder, you'll have stress concentration. So the right way to do this, if you're to do this in the real world, then you want to put a stress concentration factor right here, and then find the corresponding stress concentration factor from that table. And that would be the right sigma x. So we'll just ignore the stress concentration. So I'll just make a note here. Stress concentration. Okay, so we've got that. Now let's compute sigma z and tau zx. Let's make a copy of this. Okay, so sigma z is actually 0. It's because there is no stress in that direction. Sigma z is 0. Sigma z is upwards. Because there's no stress, there's no moment in, well, if there was a moment this way, then you would have sigma z will not be equal to 0, because now you have a moment which torques it in the direction which caused the stress, which will be in the z direction. So right there. So now we have to only compute tau zx. Tau zx the formula is T about the times rho divided by J. So in this case, the maximum stress will occur where the diameter is the smaller of the two. So Tx, T divided by 2. J is pi d raised to 4 divided by 32. So that's about it. So we've computed all these three things. I'm just going to sub in the value sigma z, tau zx, and in the previous page we computed sigma x. So I'm just going to write these equations down and solve them in terms of f. Remember that mz is here and tau x is there. Let's put it all together. So we are still in step 1. Sigma x equals mz divided by 2 pi d raised to 4 divided by 32, which will come out to be 16 m c divided by pi d cube equals 16. So mz, I'd written down the formula. It was 14 times f divided by pi t was 1 cube. Then tau cx is dx t divided by 2 pi t raised to 4 divided by 32. So that comes out to be, I did a mistake here. This is 64. It should be 32. Should be 32. And this should be 16 dx divided by pi d cube, which comes out to be 16 times tx, written down as 15 times f by pi d cube. So every second, sub in the values. It's already substituted. I just have to calculate it. 142.6 f, and for this it is 76.4 f. Okay, so we have basically got what we wanted from this. Now let's move on to step number 2, which is up this in the shear. Well, compute the tau max and sigma prime, which is the one misses stress. Step 2, tau max is, remember, it was sigma sigma 1 minus sigma 3 divided by 2. Okay, in this case, it's also it also happens to be the radius, which can be computed. So we can compute the principal stress now because we know the three stresses. You know, sigma x, you know, sigma z, and tau. Tau zx. So knowing all these, we can find sigma 3, or we can use the fact that that formula is already there for shear stress. It is sigma x minus sigma z divided by 2 square plus tau cx square. Okay, and that comes out to be, this is 0. We wrote sigma x in terms of f, tau zx in terms of f. So it comes out to be square root of 142.6 divided by 2 plus 76.4. 76.4 square equals 104.5 f. Okay, now we can also compute the one misses stress. That's also a formula in terms of sigma x, sigma y, sigma z, and tau zx. I think the formula in this case would be sigma x square plus sigma z square minus sigma z sigma x plus 3 times tau cx square. So we know that this is 0. This will also be 0. So sigma x is 142.6 square plus 3 times 76.4 f square. So simplifying this gives me 194.5. Okay, so I need tau max and sigma prime now for the last step, which is apply the distortion engine maximum shear stress theory. Just give a second and then move on to the final step.
Professor, how did F cancel out? Again, like 194.5. Shouldn't be there be F?
Can you say that again? Which part? This one?
No, the last part, like the
Oh,
194.5.
I skipped it. My bad. It should be a function of f. It won't be. Yeah, good catch. Okay, so let's plug it in. So the third step now is use MSS, which states that tau max equals sy divided by 2. Tau max we found it's 104.5 f. Sy is 81 k psi. So in this case, everything on the left is in psi. So I need to convert this to psi instead of kpsi. So that's a factor of 1000 divided by 2. And from this, we can solve for f. F comes out to be 388 lbf. So that's solution to part A. And then for DE, the formula is sigma prime is sy, but sigma prime was found to be 194.5 equals sy. Sy is 81 10 raised to 3. So F comes out to be, I get is 416 lbf. Okay, so that's the answer to part B. Let's call it A and B. So what we note is FB is greater than FA, or the predictions from DE are greater than predictions for MSS. So what D is saying is this particular machine element can bear more force, which is 416, compared to using MSS, which is 388. And that's why D is less conservative and MS is more conservative. MSS is more conservative. Okay, so we did it in 3 parts. We just have to use the same recipe for pretty much every problem. I'll have another problem where we're doing it for another loading case and see how that goes.
Professor, a quick question.
Yeah. Mm-hmm.
I just did not understand why did you say like the sigma z is 0?
Sure. So when we talk about loading a beam like this, the stress in this direction is on top is maximum, and that's my divided by I. Okay, and when we say that's the maximum, the stress in all other directions, that is the normal stress, is 0. So if you take this element here, it will have a stress in this. This stress is 0, and the stress in the plane of the paper coming outside will be 0. So we just have to pretty much do that, which is, in this case, we can think of this. This is the rod subject to M. Okay, and then since it's connected, it's anchored, it's also going to have a moment in the other way, which is going to resist bending. And so this looks very similar to this one in this plane, right? So the top part will have a stress in, this is a stress in this direction, sigma x. So similarly, this will have a stress in this direction. And turns out that this direction is that sigma x2. And the other stresses are all zero. If you want if for a stress to be in the z direction, so a situation where you get stress in the z direction is if you, so this is m mz. For a stress to occur in the x in the z direction. So let's say this is the z-axis. We would, so there are only three types of moment. There's moment in z, there's moment along this axis, which is a torque, and then there's third one, which is this way. So this will be above, this will be sort of, if you call the fingers, the torque would be acting in this direction. Torque, sorry, the moment will be in this direction. And that what axis is y. That's the moment about y. So in this case, what will happen is there will be a stress in, just like we have a stress in the x direction, what direction will the stress occur? My hunch is it should be, so we're trying to find the stress in the top. It'll actually be in, it'll be in the same direction, zx, sigma x, right? Because of the way this is, so you've got to think of this in a different plane and get it. And all of the stresses would be zero. So actually there is a maybe not now, but I will probably have a problem where if you can change the loading and you'll have a situation where there will be all three stresses, but this moment or this particular mz doesn't cause any other sigmas other than sigma x, because there's only, because there's bending in only that plane. So you need to have another moment in another direction in order to induce stress in z. And we can always do a problem related to that, but this one it won't occur just because the way this moment causes the stress. Okay, so just bear with me. I'll just bear with me. I'll try to have a problem for it. How do we go about problem that does not indicate the point of failure? Okay, so that's a good question. So here we pretty much I've told you where exactly is the failure going to occur. It's right at A. If you are not told that, it suddenly becomes a full-blown design problem in the sense you then have to figure out what the moments are as a function of distance. So think of bending moment diagrams and shear force diagrams. So you'll plot that bending moment as a function of distance. You'll plot the shear stress of the shear force as a function of distance. Identify which part is the critical part, and then use that to then apply the theory. So there's a bunch of calculations which goes just before this step, which is you need to do the BMD and shear force diagram. After you do this, then you can start analyzing it. But this becomes a kind of for this particular geometry, I think it becomes kind of slightly more tedious to solve it. Now, so that's why I gave it to you. And also, if this was actually a design problem where you're trying to do this, you not only have to do the bending moment and shear force diagram, you also need to consider the stress concentration at all these points. And then you'll have to go through the table. And then remember, the table is not, well, so it's a plot, right? You need to pluck it from that. You probably want to approximate that plot by an equation so that you can quickly plug and check. So it becomes very tedious, but it's definitely doable. In fact, if you do this with ANSYS or any software, it will pretty much do what calculations we are doing here. It will figure out it'll give you the sigma x sigma y, sigma z, all the stresses. So you really don't take the effort to do this by hand nowadays because you have this software which does these calculations for you. But yeah, that's a very good question. If you're doing senior design, this is the kind of analysis you want to do, probably with ANSYS and not by hand calculation. Okay, next question. Okay, so I don't know how much time I have, but we can try to set this up. This is it.
First, can we do this example by the where we show the other way, like to find the moment and forces by the cross product thing, if that's feasible.
Oh yeah, I can do that. Yeah, I can compute it both ways. In fact, yeah, that's absolutely fine. You just write R and F and it'll be easy. Okay, so I'm assuming that I just have 7 minutes. So I'm going to start this, but I probably won't be able to finish, and maybe I can set it up so that you can try it yourself and then come back on Monday. So the shaft is shown below is subject to a force F, load P, and a torque T. The material used is aluminum with a yield strength of 276 MPa using the table shown below and design factor of ND equals 4. Select a stock size for the shaft and compute the factor of safety. Assume von Mises stress as the failure. Okay, so a couple of things. So first of all, you already told that this is the point of failure. So we don't need to really do the shear force bending moment diagrams are given to us. So for this particular element, we need to identify the stresses. That's step 1. So 1 for A. We can draw the stresses. So you can see that this element is in the, again, the same direction, XZ plane. So you would have sigma X, sigma Z, and then shear stress.
So, Professor, just want to confirm, this element is on the top of the rod, right? It's not on the wall.
It's on the shaft, yeah.
On the shaft, right? Got it.
Yeah, it's right on the shaft.
Got it.
So it's like this.
Got it. Makes sense. Thank you.
Yeah. Okay, so we need to compute sigma Z, sigma X, tau ZX. The second step would be to compute sigma prime, which is the von Mises stress. And then the third step is, I think there's a design factor here. So we need to say that sigma prime will be sigma max. And sigma max is, we can find that because we're given the design factor. So in this case, sigma max would be, using the definition for design factor, it would be SY divided by ND. So 276 divided by 4, that comes out to be 69 MPa. Okay, so it boils down to part 2 and part 3 are pretty simple. It's just boils down to number 1. How do you compute the stresses? So what we do is we do something similar. We need to identify what are the moments and what are the stresses created by those moments. So let's just do that. Can we draw this element? F P T, and then the axes are X, Z.
हमने चली गई.
Okay, so we can identify some of the values directly without doing any calculations. For example, torque. The torque is already given, and it is, if you curl the fingers of your right hand along the direction of torque, then the thumb gives you the direction of the torque. So the torque is, as a vector, is T, magnitude T, and it's in the negative X, x direction or negative I direction. So it's going to be, so if you curl your fingers along the torque, your thumb will be in this direction. That's the value for the torque. So the force P here gives rise to an axial force, right? It's going to cause an axial stress. So we don't really need to write it as anything here. We just have a P of, can just write P equals P of I. Okay, and then the force F is, this is the vector, is along the negative y direction. So F times J. Okay, so we've got that. Now we need to compute what is the moment at this point A. So let's take this to be L. So we have the, I'm just going to call, well, let me call that M. Vector is R cross the net force plus, now remember here, there is, besides the force, there's also a torque. So I need to put all the torques here. So that moment is the sum of all the moments due to, or torques due to R cross F and then T. And so R is, as you can see, it's L times the, L is in the direction of X. So Li cross F, there are two forces. There is Pi, and then there is P negative I. Okay, plus T, oh, sorry, my bad. F is Fj plus T minus I. So L I cross, but first component, when you do I cross I, that's going to be 0. Then you have I cross J. The I cross J is K, so minus FL K plus T times minus I. So these are the moments. You would have two moments. One is FLK, which would be, see here. So since it's in the negative K direction, it's going to be this way. And your thumb should point in this direction. So that's T. What do they call that? MZ. Okay, I'm out of time. MZ equals minus FL. Just put FL K because I already took care of the direction there. FL. Okay, so that's the moment. Now, before I leave, if you want to try this, you need to compute sigma x, and you'll see that sigma is a function of, there are two things. They will be due to M plus due to F. This is an axial stress. And then you see tau Zx will be due to torque. And then you'll see that sigma Z will simply be 0, just like this. Okay, just revise what we were doing. We were trying to solve this problem on failure theories. Here the shaft is subjected to some loading. There's a force F. There is a axial load P, and there's a torque T. And then you given the values. You're given the yield strength. You're given the design factor. And you're told to select a stock size for the shaft, and then compute the factor of safety, assuming one misses stress. So the stock shaft is this. So this is like, if you have a catalog, and catalog has a number of different sizes which you can choose. This basically alludes to that. How will you choose the stock size? So what we do essentially is, based on the failure theory, we'll predict what the maximum stress each of these sizes can take. And once we have that number, we can then pick a stock size. Okay, so this is one of the design problems, so to say. So first step is to do these three things, which is, first we need to figure out the stresses for the element A, which is shown here. And as I said, that element is it's on the top. So the top is in the XZ plane. So you can see X is there, Z is there. And so it's the XZ plane. So we'll have three stresses: sigma X, sigma Z, tau ZX, as I've shown. Once we compute those, we can find the one Mrs. stress, sigma prime. And once you know the one Mrs. stress, we need to equate that to the maximum stress. But the maximum stress in this case would be the yield stress divided by the factor of safety, which is 69. So we're looking at 69. So we did part 3. We just need to figure out what 1 and 2 is. Okay, so let's go and do step 1, which is probably the most important one, and that sets up for 2 and 3. Okay, so here I've redrawn that figure of the 3 forces acting, two forces and one torque acting on the cylindrical shaft. Okay, and what I did was, instead of doing it by visualization, I decided I'm just going to use vector mechanics. So I drew x, y, z axis. These vectors I, j, k are unit vectors in the x, y, z direction. So the torque you can see is along minus I. Again, the way you get this is you curl the fingers of your right hand along the torque, and your thumb gives the direction of the torque. So my thumb in this case is pointing along the negative x-axis, you can see there, and so it's negative I. Negative x-axis. P is obvious, it's pointing in the direction of the positive x direction, so it's pi. And then the force F, as you can see here, is in the negative y direction, so it's negative fj. Okay, so this is an equation from vector. That's the definition for moment. It's r cross f plus any torques you provide. So these are all vector equations. So I write the vector equation for r. R is this. Right, it's along the x-axis, so L times I. Pi is this, minus Fj is something I wrote down earlier, and then we have torque is in the negative I direction. Everything is just substituted from here. Okay, so if we do math here, we can see that I cross I is 0, I cross j is k, and so the net moment is due to F is Fl magnitude, and it's in the negative k direction. So by k, I mean z. So this is the direction of the moment. It's in the negative z direction. Again, if you want to find the direction of this arrow, which I've drawn here, okay, why is this arrow this way? What you can do is, here this is a reverse problem. We know the direction of mz. It's along negative k. So you point your thumb of your right hand towards mz, that arrow. Okay, if you do that, your fingers will curl along the direction of this arrow which I'm showing right now. Okay, so it means that it is clockwise as seen from the left. That's why I have what I have. Okay, so this is mz, and then this is as it is. Okay, now we've got that. We are now computing the stresses at A. Sigma x, sigma z, A. Okay, so the stress sigma x will be, I'm just going to fill this blanks now, will be due to m, so there'll be m z y divided by I. Okay, and you can see that if m is applied the way it is shown, the top surface is going to be under tension, right? Because it's going to, the shaft will be sort of convex. Otherwise, it would look like a inverted U, or it will be this way due to this momentum. That's why it will be positive stress for the top part, tension. And then P divided by A is the stress due to axial load. And we know that that stress is positive no matter what, right? It's always stretching, it's not compressive. So that stress is also tensile. In fact, it's tensile for A, it's also tensile for the bottommost layer, which is positive. Okay, the shear stress, tau Zx, will be the torque times rho. In this case, rho is R. R, I'll just write that as half of the diameter divided by J. And then sigma Z is 0. That is, there's no stress in this direction, which is out of the plane of the XY plane. Okay, so let's take this and sub in. We'll move things around, make it a little bit more cleaner. Okay, let's substitute the values. M is F times L. Y is the distance from the neutral axis. So that's going to be D divided by 2. I plus P divided by A. This will be T. It's circular. Oh, my bad. I should, yeah, D over, yeah, that's the radius. Right, so if you have a circle, this is the neutral axis. That's R. So that will be D divided by 2. Let me copy these equations. Okay, now we want to sub in whatever we know about these, whatever we have in terms of forces. So let's sub in those values. So what I have here is P is 9 kilonewtons, so 9,000. Mz is, well, F times L. F is 1.75 kilonewtons, so 1750 Newton. Then we have L. That's also given. It's 120 mm. So it's 1 point divided by 1,000, so 0.12 meters. And then we're given T, that is 72 Newton meters. So what I would do is I would sub that in these formulas and get me sigma x will be now 1750 times 0.12. He is 9,000 A. Tau Zx equals 72 times 2J. Yes. $110. Okay, so note, we don't know anything about I. As of now, we don't know anything about D, J, I. Those are unknowns. We need to compute the maximum, okay, we need to compute the one misses stress. So there's a formula which relates one misses stress to sigma x, sigma y, tau z, xy, but in this case in the xz plane. So the formula would be similar. It will be sigma x square plus sigma z square minus sigma z, sigma x plus 3 tau x z square. But sigma z is 0, sigma z, so that's two terms will go away. So sigma prime would be sigma x square, which I'll now substitute from here, 210 divided by 2I plus 9000 A plus 3 times 72 divided by 2J square. Okay, let's call this 1. Call this 2. From 1. From 2.
Why is it 3 tau x?
That's the formula, yeah. Yeah. Because the problem is to we want to assume that one misses stress is the failure criterion. Okay, so we have this expression which is just long, and we don't know anything about D, I, A, and J. So what we do now is, now that we have those values, we can now go to this table. You can see that the table gives us, for different stock size, it readily gives us what A is, what I is, what J is. So if you, for example, if you choose this stock size, that's your A, I, J. Okay, so what needs to be done is we need to sub in the values for D, I, J, A from that table and compute what sigma prime is. And so I used a MATLAB to do this computation, but you can use Excel too. You just need to tabulate. So what I did was I put in the value for these three numbers, D, T, A, I, J, in that formula, and I computed what the corresponding sigma prime is. Okay, so it gives me a bunch of sigma primes. Okay, now that I've got sigma prime, what I need to do is look at the failure criterion. The failure criterion is that sigma prime should be equal to sigma max. It cannot exceed sigma max. And sigma max is SY divided by D, which is 69 MPa. So as long as the sigma one misses stress is less than 69 megapascals, that stock size is good, it's safe. So we need to go through this. So 10 raised to 6 is MPa. So these values here are in MPa if you get rid of 10 raised to 6. So you can see this will, if this stock size will have a stress of 1740, much greater than 69. Just keep looking down. You have 71, 60. This is the case. So 71 is a little bit greater than 69. The next one is this. So it looks like this is the shaft stock size we need to choose. Is less than 69 MPa. So we pick that based on the criteria we have. And then the final question asks us to compute the factor of safety. So part B. So for part A, the answer is stock size of 42 cross F, oh sorry, 5, because as sigma prime is, which is 16 MPa, is less than 69. And for part B, we need to find the factor of safety now. So remember, the factor of safety is computed after the design is complete, right? So we've completed our design, and the factor of safety is the max, the max stress, in this case, the yield strength, divided with the maximum stress. Yes. So SY is 276. 276. And the maximum stress now is right 60.4, not 69, because we're going to use a stock size of D cross T of 42 cross 5, 60. So the factor of safety comes out to be 4.56. I want to be precise, 42. So N equals, okay, which is, by the way, greater than the design factor, which was 4. Yeah, it's more safer. Yeah, you cannot, if you had used the 71, you would have seen that the factor of safety would have been less than 4, and that goes against your the spec. Right. Somebody chooses that. You can also choose a factor of safety. You see that the bigger the factor of safety, the bigger are your dimensions. So for example, here you can see it's 42 cross 5. The diameter is 42, thickness is 5. Compare that with the first entry, which is 12 cross 2, which is 12 diameter and thickness is 2. That's a smaller stock. So it will be lighter than the 42 cross 5, but it's not strong enough. So it just goes by rule of thumb, like for aircraft which fly and you're carrying the weight, you probably want to go somewhere like 2, and I think that's what they use. If you want to look at a civil structure, like a building or a bridge, where things are in stationary, you just want to put a factor of, I don't know, 8, 10, something really high, because you want to, withstand a lot more loads. So it just, I guess, by experience. Now, one thing you remember that if you've done this problem on stress concentration, we saw that the stress concentration, I should go there. This is actually something which you want to be mindful when you design. So it's not here. If you look at those stress concentration, okay, so for example, let's take this. Okay, when you design this and there's a fillet, right? The fillet, let's take, for example, right here. So let's say that because of the design, you have a stress concentration, and then you have a KT of 2, right? The KT is 1, yeah, it's exactly 2. So you can see that the way this KT comes in the equation is it's right there. What does it? It does, it basically reduces your strength by a factor of 2. So now if you have a factor of 2 in your design factor, because of this KT, it's going to become a factor of safety of 1. And that's why you don't want to be probably close to 2. So if you want to be at 2, then such things will reduce the factor of safety by that whole factor. The KT will reduce it by the same number. And that's another reason why you want to have a highest factor of safety, is because of stress concentration. That will just reduce the strength. And it's usually what happens is if that part is very critical, like, when you design things, if there's redundancy, there's parallel members, and if one breaks and others can take the load, then you can be a little bit more less conservative. But if everything stands on one pillar, and that pillar is like in a bridge, right? The pillar is important. If that pillar breaks, if the whole bridge collapses or part of the bridge collapses, then you clearly want to have a very high factor of safety, because it's like a series system where one thing breaks, the whole thing comes down. So that's another reason why you want to have a high factor of safety, which conflicts with your metric of being light. Okay, so that's basically is a question, and I would say that questions like these are kind of have been hard in the previous semester, because there's need for some visualization to figure out the stress and resolve and so on. So I'll have some questions in the homework which will help you to try these things out yourself.